Hello, everybody. My name is Panagiotis. I am a mechanical engineering student at the University of Western Macedonia. And today I am going to present you our work in chaotic navigation and achieving uniform exploration through area segmentation. I'm going to start by the motivation behind chaotic path planning research and the objective of this work, continue with the path planning system and the area segmentation technique that we used as an optimization technique. Then present you the simulation results, conclude this presentation, and have some discussion about future research ideas. I'm sure that many of you are familiar with chaos applications. One of them is path planning. Path planning itself has many applications as well. Floor cleaning devices, firefighting devices are some of them, but some more relevant are surveillance of terrains, terrain exploration, and patrolling. The objective here is to generate unpredictable motion trajectories for the agent. For example, if the agent is in a potentially hostile environment and it's targeted by an adversary, it must maneuver in ways that cannot be predicted and confuse the enemy, but also maintain an efficient exploration of the given area. For example, as well, if an agent must surveil an area unpredictably, if, for example, the agent is defensive, the motion of this agent shouldn't be periodic or could be known by the adversary, because in that way our agent could be avoided by the enemy. This work builds upon previous works by considering a limitation in the possible movements of the agent, and in that way tries to eliminate sharp corners and makes the motion smoother and more applicable to a real robot. It also improves the coverage percentage of a given area, and also, and most importantly, the consistency of achieving this coverage. This is achieved by the segmentation technique that we used. To create the chaotic navigation commands, the Renyi map was used as a chaotic source. K was chosen to be 19.99, and the trajectory of the map is shown at the bottom of the slide. We can see that the map exhibits constant chaotic behavior as well. It can be verified by the Lyapunov exponent diagram for any k over 1. Now, the robot has 8 possible directions and 8 possible orientations. The map generates numbers between 0 and 7, which are generated by the relation shown on the right-hand side of the slide. And as you can see, for 20,000 iterations in this histogram, these numbers are generated uniformly. If bias is desired in some application, this relation can be accordingly modified. So at the beginning, we thought of letting the robot free and unrestricted to move, but we saw that the motion was too sharp and made it difficult to apply that idea to a real robot. We restricted then the movements to front, front left, and front right, and we introduced a variable which we called orientation, that it is what determines the 3 possible movements. As you see in the left-hand side, if the orientation is 0, the 3 possible movements are 7, 0, and 1. And if, for example, is 3, the 3 possible movements are 2, 3, and 4. The orientation itself changes according to the previous movement of the robot. If the previous movement of the robot was 0, the orientation remains 0. But if the previous movement of the robot is, for example, 1, the orientation changes accordingly. Also, the algorithm is such that in each iteration, the robot is prompt to make a move. If the movement is not allowed, for example, if the robot is prompt to cross a boundary of the given area, the robot stays at the same place and changes its orientation. This technique is similar to mirror mapping. To optimize this technique, we divided the area into equal sub-areas. We introduced a 100 by 100 area to be explored and divided it into 4 and 16 equal sub-areas, developed 2 and 4 different patterns in each approach respectively. Regarding the threshold of moving from one sub-area to another, the first approach was giving the robot a specific coverage target value, which it needed to achieve before moving on to the next sub-area. And here the main evaluation parameter is the steps that the robot needs to achieve this coverage value. The other approach was giving a specific number of steps to the robot, and the coverage itself was the evaluation parameter here. The evaluations that I'm going to show you now regard the second type of threshold, because having an evaluation parameter, having the coverage as an evaluation parameter is more easily interpreted. And also one of the patterns is presented for the 4 and 16 sub-area case. And as you can see, we introduced two more evaluation parameters, the mean visits and mean visits of visited. Here you can see a demonstration of the robot's path. We can see that the path is smooth and visits almost the whole area, but there are some areas that are not visited and others that are visited multiple times. This can be seen also in the simulations here. We can see for 5,000 steps that the coverage is about 35%. For 10,000 steps, the coverage is about 59%, and the mean visits are 1.4 and 1.7 roughly respectively. We can see that the coverage here is not uniformly distributed inside the area, and there are areas that are visited up to 10 times and others that are not visited at all. In the bottom graphs, we can see that the coverage is not uniform, and there are areas that have zero coverage and others that have more than 80% coverage. This is true for the 15,000 steps simulation. The coverage is about 76 now, 76%, and the mean visits about 1.9. Note that the initial position for all the simulations are the bottom left cell, and the initial orientation is random. As I said before, the coverage was not uniform, and most importantly, was not consistent. As you will see in a few slides, the coverage was not as consistent as it should. So we divided the area into 4 and 16 sub-areas, and here you can see two of the four patterns for the 16 sub-area case. We can see that the robot visits the whole area again, but now there are little areas that are not visited at all, and even less that are visited multiple times. Here in the simulations, you can see again that the coverage is increased. In the parentheses with the red color, you can see the values of the coverage, the mean visits and mean visits of visited for the previous case, for the one whole area case, but for the same amount of steps. So we can see that for 5,000 steps, the coverage increases 4%, about 4%, but the mean visits of visited are decreased. The same applies to the 10,000 steps simulations. The coverage increases to 61.6%, and the mean visits of visited are again decreased. For 15,000 steps again, the coverage goes up to 76.5%, and the mean visits are again decreased when compared to the one whole area case. We can see that there is an improvement in the absolute value of the coverage, but what's more important is the consistency of the coverage achieving and the uniformity of the coverage inside the area. This can be seen in the graph here. We can see with the red line the one whole area case, and with the blue line the segmentation technique case. With the dashed lines, it's the minimum and maximum performance of the robot. We can see that in the segmentation technique, when using the segmentation technique, the mean visits of visited are constantly lower than the one whole area case. And another another important thing is that the deviation between maximum and minimum performance of the 16 sub-area case is much less than the one whole area case. This is true for the coverage itself, which is the main evaluation parameter. We can see that the coverage for the 16 sub-area case is constantly higher than the one whole area case. But as I said, the thing that is more important is that the difference between maximum and minimum performance is decreased when compared to the one whole area case, where the deviation is higher. So, to conclude this presentation, in this work, a chaotic navigation algorithm was developed, which had the desired chaotic behavior. Restricting the motion of the robot made the motion smoother and eliminated sharp turns, and it made this idea easily applicable to a real robot. And finally, using the area segmentation technique, increased the percentage, the coverage percentage, and also made the coverage more uniform. But more importantly, made the coverage achieving more consistent. So for the future, there are several differentiations that can be added to the system, and also many problems that can be considered for further study. For optimizing this technique, there are several techniques that can be used, such as pheromone, which can be directly implemented in that algorithm. Also, introducing obstacles and unpredictability in the environment would make this idea applicable to a larger scope of applications, and would make the realization of this problem much easier. And as I said, another future suggestion is making an experimental realization of this idea, so we can test the performance in a physical environment. Also, all the above can be considered while using multiple collaborating agents and 3D environments, for example, in UAV applications. And finally, this idea can be applied to non-physical environments too, such as in encryption. Here are some indicative references of our work, and now I would really like to thank you for your time and attention. Thank you very much.